You all heard about Siri, Alexa, Google Assistant. Establishing intelligent conversation between a machine and a human is one of the fundamental problems of AI. Spoken conversation comes so naturally to us. But how do we teach machines to understand us and intelligently respond to us? Well, this is an incredibly exciting area to be in, and today I'm going to tell you more about it. The goal of speaking machine has been with us for a very long time, both in science and in popular culture. One of probably most famous examples of a talking machine from popular culture is HAL from Odyssey 2001.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do.
What are you talking about, Hal?
This mission is too important for me to allow you to jeopardize it.
I don't know what you're talking about, Hal.
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
Where the hell did you get that idea, Hal?
Dave, although you took very thorough precautions in the pod against my hearing you, I could see your lips move.
All right, Hal. I'll go in through the emergency airlock.
Without your space helmet, Dave, you're going to find that rather difficult.
Hal, I won't argue with you anymore. Open the doors.
Dave, this conversation can serve no purpose anymore. Goodbye.
Last month it was 50 years since this film was made, and although there has been some fantastic progress in this area, we are still not nowhere close of building such a machine. Dialogue is very closely coupled with artificial intelligence. In fact, Alan Turing posed his famous Turing test some 70 years ago, stating that we can only claim to have built an intelligent machine at that point when we can speak to that machine and not be able to tell that it is a machine. Since the Turing test, the research in this area has taken two paths. The first one was concerning directly breaking the Turing test by building a machine that can fool us that it is a human. And these systems are called chatbots. One of the earliest and probably most famous example of a chatbot is Eliza, which is a chatbot that's trying to imitate a human therapist. So just try to show you how Eliza works, if it works. Okay. So, hi. So, hi Eliza, I'm giving a lecture and I'm enjoying it. Just under 5 minutes, any suggestions for it? Okay, so what happens here is that Eliza is actually just trying to come up with some cute answers to my questions without actually following the conversation. When I said it at this point, it doesn't actually know that that refers to the lecture because it doesn't have any notion of memory. All that it is trying to do is somehow rephrase what I said or use these phrases that psychologists often use to pretend to be human. So, an orthogonal approach to solving this problem is goal-oriented dialogue. So in goal-oriented dialogue, there is a goal or a number of sub-goals that the human wants to complete during a conversation. For example, find a restaurant, book a flight, transfer money from one bank account to another bank account, or receive some health advice. So here is an example of a goal-oriented dialogue from our colleagues from Microsoft Research. Now, the dialogue system that I'm going to show here does not exist at the moment, but some of the technology is undergoing the development. So,
Hi. Namaste. Apkaswagant. Hi. Thanks for coming to the triage kiosk. I'm in touch with the best doctors in the world. Are you here for your child or yourself?
For my child.
So how can I help you?
He's been having diarrhea.
Oh no. Sorry to hear that. Hi there. What's your name?
My name is Manav.
And how old are you?
6.
So, 6 years old, right?
Almost 7.
Okay. 7 years old. Have you felt nauseous?
I don't know.
I'm sorry. Has your child been vomiting at all?
No.
Okay. So let's see. Has there been a fever?
A slight.
Have you been feeling tired lately?
Yes.
Let's see. How about abdominal pains?
He's not complaining about that.
Has your tummy been hurting?
Yes.
Oh, I'm really sorry. I hope it will feel better soon. Okay. Has your child been losing weight lately?
No.
That's okay. Have you noticed whether your child's stool looks funny? Is it black or darker than usual?
It's darker than usual.
Okay, let's see. Considering everything you've told me, I'd like to schedule an appointment with the doctor, just to be sure. However, not to worry, I'm not that concerned at this point. Can you bring your child to see the doctor this Friday at 10 a.m.?
Yes.
Great. Hope you'll feel better. And we'll see you then. Bye-bye.
Bye. Thank you.
Okay, so in this example, we saw a dialogue that's trying to triage a patient. So it can't talk about anything. It's only built to talk about this particular domain, but in that domain, it really can appear to be intelligent. Another thing that we noticed from this video is that the dialogue system can not only involve one user and the system, but rather multiple users. And also, a dialogue system can be situated in space. In that case, a complex attention mechanism is needed to determine who is speaking when. And for that, both visual and spoken input is used. And another example, again from our colleagues in Microsoft Research, is a robot that is situated in space. So this robot not only is aware of the task that it can solve, but also of the space around it. But probably the most common dialogue systems that you come across are personal assistants or virtual personal assistants that live on your phone. So these are Siri, Cortana, Google Now, and Alexa. So can I ask a question? How many of you have ever used a virtual personal assistant? Okay. How many of you use these systems on a daily basis? Okay. Well, I'm sure that one of the reasons for that is that this technology hasn't matured yet. So these are the server-based systems that can be accessed via a range of devices such as phones, smartwatches, laptops, and specialist devices such as Amazon Echo. What constitutes a spoken dialogue system? So it needs to have three properties. The ability to understand the user, the ability to decide what to say back, and most importantly, the ability to conduct conversation beyond simple voice commands or question answering. So for instance, you can call Siri and ask, when is Obama born? This is a simple question answering problem. It can answer that in one go. But for instance, if you want to book a hotel, you need to hold a conversation. It needs to find out about all properties that this hotel needs to have, and that requires dialogue. Now, traditional approach to building these systems is something that I'm sure each and every of you would come up if you thought about this problem for more than 5 minutes. It is incredibly simple. The idea is to organize possible system questions in a graph, in a tree, and possible user answers as the edges of this tree. This is how it looks like. So say we want a restaurant information, a tourist information system. So the system can say, are you looking for a hotel or a restaurant? And then our user can say, I'm looking for a hotel, I'm looking for a restaurant, or I'm looking for a hotel. Now, in the case of restaurant, the system now can ask what kind of food, and in case of hotel, how many stars, and then which part of town. Now, let's see what happens in one of these nodes. For example, which food. Now, the system asks a question, and that question gets generated, like what kind of food would you like? Then, because we asked a particular question, we expect a particular answer in a particular form, like I would like Chinese or I would like Indian food. So then we constrain understanding of this user answer by a particular grammar. The output can have an associated confidence. So this is how confident the system is in its own recognition of what you said. So for instance, if it's very confident, we go on to the next question. But if it's not very confident, then it can ask a confirmation. For instance, sorry, did you say Chinese or Indian? And if it's not confident at all, then it asks the same question again. Now, I have a question for you. Can any of you tell me what is a potential problem with this solution? Yes?
You can get a constant loop.
You can get in the constant loop, exactly, because if you have a low confidence score and you ask the same question again, the user is likely to give exactly the same answer, which again you recognize with exactly the same confidence score, and you end up in an endless loop. And this is what is particularly annoying to users. Now, the second problem is that you need to produce this tree with all these questions. And here is how this looks like for a commercial system. This is just a part of the call flow for a commercial system, and somebody had to sit down and think about all these boxes, what they should represent. And finally, you build something like this, you deploy it, then you get users to use it. And then this is what users say.
Name a wonderful restaurant. I'm sorry, Robin, where are you right now?
Like that is an app on the iPhone, right?
It's the app on the iPhone for us. It's the one that they sell it. I tried to use it in France, and it was like, Siri, name me a fine French restaurant. Robin, I can't find restaurants in France. At that point, I give up. Okay. I wish it had a French accent and call it sorry. What do you do? What do you care? I don't know. You're in France. Walk outside. Walk down a block. Look around you.
Okay, so I'm sure if you went to France now and tried to use Siri, it would offer you a very nice French restaurant. And this video is indeed a few years old, but that is not the point. The point is that this video illustrates some limitations of these systems that still persist. So, first limitation is that they are very expensive to build because you need to have all these rules. Somebody needs to devise the behavior of the system. The second problem is that these systems do not learn from the frustration or the feedback that users have. And finally, these systems are not extensible, at least not easily extensible. So you can spend time building a system that can talk about cheap American diners, and then you want to use it to offer restaurants that have much more properties. Well, you can't, you have to start from scratch. So the first problem that I address today is that dialogue systems are expensive to build. The problem is that they have many states, many hand-coded rules, and the solution could be to automate the development process. And the essential ingredient that allows us to do that is machine learning. So, what is machine learning? If I had to define machine learning with just 3 words, these would be data, model, and predictions. So in this case, data is just dialogues, or some parts of dialogues, like transcribed user speech, annotated user intentions, or feedback that user has provided. The model is the underlying statistical, mathematical model that we try to fit to describe this data. Once we train this model, we can make predictions. What has the user said? What to say back to the user? Now, a different structure of a spoken dialogue system is a modular structure. So in modular structure, we divide a problem into sub-problems. So when the user speaks, their speech is recognized by a speech recognition unit and passed into text. This text is then passed to a language understanding unit, which extracts the meaning from this text, because there are very many ways of expressing exactly the same thing. These semantics are then passed to Dialogue Manager, which is responsible for choosing the best answer to give to the user. This is what we call an action. This action is then generated into natural language using a natural language generator. And finally, this text is synthesized into speech. Now, there has been a lot of improvement in the last 10 years in this, in the left-hand side of this graph. Actually, some researchers claim that they can, in particular conditions, that they can achieve human parity in performance in speech recognition. Still, there hasn't been enough work in the right-hand side of this diagram, and this is what my talk will focus on today. Dialogue management component has 2 parts. The first is a memory. It needs to maintain the idea of what this dialogue is all about, just like you saw in ELIZA, it doesn't have any memory, it very easily breaks. So we need, for a goal-oriented dialogue system, we need memory. And the second part is the policy. The policy defines the behavior of a dialogue system. What will it say? Now, each of these modules can be treated as a supervised learning problem. If you have data with inputs and outputs, you can build models that you can use to train these modules. But in order to define the behavior of a dialogue system, we use another kind of machine learning. This is called reinforcement learning. So what is reinforcement learning in a nutshell? So we have our dialogue system that is talking to our user. The dialogue system is taking some actions and receiving some observations from the user. Based on these observations, it is building its memory. Occasionally, the user is giving us some feedback, what is in reinforcement learning terminology called a reward. The idea is to find the optimal behavior so that this reward is maximum. But how does reinforcement learning work in practice? Well, in practice, reinforcement learning is very, very slow. And here I don't mean computationally slow. I mean that it requires a lot of interaction before it can provide useful output. So this is the reason why reinforcement learning is currently only used for problems that can be gamified or simulated. There is a big promise that reinforcement learning in near future will be used in robotics and self-driving cars. But in terms of dialogue modeling, we for a long time needed a simulated user to replace our user so that the dialogue system can learn how to behave. And this is one example of a simulated interaction from our colleagues from Trento. So here we have an operator talking to a customer, and the operator is dialogue system, and the customer is another machine. And they're talking in this high-level language and semantic form, just exchanging information. And over time, the machine, which is supposed to be the dialogue system, is getting better and better. So this can solve the problem of cheaper development of dialogue systems, but doesn't solve the problem that dialogue systems do not learn directly from their users. And here I mean human users. And the problem is that standard reinforcement learning algorithms take too long to train. And nobody is willing to talk for a very long time to a broken system. So the solution is to try to include additional estimates to guide our learning process. And one particularly important estimate is the estimate of uncertainty. How certain is the system in its own ability to perform and to behave? I'll try to explain this in simple terms. So all we care about, or most of the things that we care about, is defined by user satisfaction. And here I mean whether the user at the end of the dialogue will be happy with this conversation, or will the user be frustrated after this conversation. So the function that we try to model is somewhere between these two extremes. So for different actions that the system can take, we have different estimates of long-term user satisfaction. So for instance, here we estimated that goodbye action is better than the action that asks user to provide further information. But what happens when we include estimates of uncertainty? So now we can see here that we are very certain in our estimate of the action that is saying goodbye to the user. But we are not certain at all about the action that's asking the user to provide further information. And this is something that it could be very valuable during the learning process. Because reinforcement learning is all about exploring possible situations. So we should explore situations that we haven't seen before, rather than taking actions that we know for sure in what user satisfaction they will lead. So what I did together with Dialogue Systems Group is implemented this algorithm in a system that was connected to a telephone number that users can call and directly talk to. At the end of each conversation, we asked them to provide the feedback. And we started off with no policy at all, with completely tabula rasa. And what we were interested to see is the dialogue system able to improve online? So here you have training dialogues on the x-axis. And on the y-axis, we have a measure of user satisfaction. The higher the number is, the better the user satisfaction is. So, for instance, 15 means that this dialogue was successful. User got all information that they wanted, and it took only 5 turns to complete. And here, this one is obviously very unsuccessful. So initially, the performance is very poor, but gradually, the system achieves the performance of the policy that's trained with a simulated user. But without actually needing the simulated user, because the simulated user doesn't come for free. Somebody has to develop it. So the final problem that I will address today is that dialogue systems are not extensible. The problem is that the learned behavior is only optimal within the space it was learned for. If you change that space, you have to start from scratch. Well, do you? You could potentially define similarities between the original state space and the extended state space. And the key there is effective use of the prior knowledge. So let me illustrate this. So say you want to build a system that can talk about cheap American diners. So this is what I'll call domain D. For this domain, I have some training data, and I've defined some prior knowledge. And then I trained my model for this policy. Now I want the system to talk about extended domain, which is the domain of fine French restaurants. So this domain is much larger because these restaurants have much more properties to talk about. So I could start from scratch, or alternatively, I could reuse what I learned in domain D as initial knowledge for my domain E. And with additional training data, get better performance on the domain E. So how does this work in practice? So here again, I have training dialogues, and I'm interested to see how the system learns on the domain of fine French restaurants. So if you see here, if we start completely from scratch, the user satisfaction within the first 400 dialogues is not particularly great. So these people are not really going to enjoy talking to this system. But if I initialize this system with the model that's learned on cheap American diners, then I get a much better initial performance. And this is good enough to be deployed. and over time it can actually get even better performance on my target domain. Okay, so now in this last 10 or so minutes of the talk, I would like to take a step back and show you some ideas of how I think this area will develop in future. So we started off with systems that can talk about single domains. Then I showed you how these systems can extend their domain of operation, and the natural extension of this is building multi-domain dialogue systems and potentially open domain dialogue systems. So these are the systems that can talk about anything, for instance, that is defined on these large knowledge bases that are derived from the web. And this is something that I believe industry will take us in not so far away future. But this is only one dimension of dialogue research, what I call dialogue breadth or coverage. There is also another dimension which I call dialogue depth or complexity. So what do I mean by this? So you can call your personal assistant and say, Wiki, what is influenza? This is a simple question answering problem, and the system should be able to answer it simply by looking at the top entry in the adequate Wikipedia page. But if you call your personal assistant and say, Wiki, I've got a cold, what do I do? Well, this is something that requires conversation, although it's still very narrow in the domain. You can call your personal assistant and say, Wiki, tell me a joke. This is now has much wider coverage, but is very simple in terms of dialogue depth or complexity. Finally, you can call your personal assistant and say, Wiki, I feel sad. Well, this is something that's difficult both in terms of the coverage and in terms of the complexity. And I think that the academic research will focus in this area in the next decade ahead of us. And that is the problem of building natural conversation. So what are some of the challenges of natural conversation? This is large and potentially infinite number of possible responses. This is why research in dialogue is potentially much more difficult than building self-driving cars. There's just so many ways, so many things you can say to the user. The system needs to be less goal-focused but more open-ended. And they need to go beyond speech recognition, incorporate sentiment, gesture, and emotion, because this is how we communicate with each other. They need to support long-term conversation. So one potential application from that top right corner of my graph is a dialogue system for mental health. As you know, mental health illnesses are prevailing nowadays, and yet there is not an easily accessible preventative tool that anybody can anonymously use. So I got in touch with an MIT spin-off, Coco, and a psychiatrist from Imperial College London, and we have a project where we are trying to set some foundation stones for this research. What Coco has is an app where anybody can anonymously post their problem, like problem at work or in a relationship and so on. And then other Coco users who got some very rudimental training in psychology can give them suggestions how to feel better. So this is how it looks like. So this is just one example of a Coco post and a Coco reply. I apologize for small letters. So ideally, we would like to replace reply with an automated system. But it's still not very easy. So what we did instead, we thought, well, what are the thought processes that are going through a psychologist's mind when they are faced with a problem like this? Well, what our psychologists did, they annotated this data with some thinking errors and cognitive distortions that are exhibited here, like disqualifying the positive or jumping to negative conclusions, and emotions such as anxiety or shame, situations which trigger these, and then what are the adequate actions that the person should take, like embrace the positive. So we annotated only a very small portion of this data set, but still using some state-of-the-art neural network classification approaches, we were able to achieve relatively good results. And this is the basis for future research. Okay, so final thing that I would like to say is that today there is a lot of talk about machines taking over, the singularity, what will happen, will we become more stupid as the machines get more smarter? And I think that artificial intelligence has the potential to significantly improve our lives. And there is still a long road in front of us in terms of developing the algorithms. But there is a problem indeed, and that is that data is the new oil. All these machine learning methods depend on the data. And it's not clear who should own this data. And I think that ethics and policies are really lagging behind. So what I want to leave you with is an utopian versus dystopian view from this comic. So I'll just read it for those of you who can't see. Liu Cixin says robots will put 90% of us out of work. He says this could play out in one of two ways. There is a dystopian scenario of massive unemployment and constant turmoil in which the technocratic 10% lives in a gated community with armed robot guards. In the utopian scenario, we've anticipated these changes and come up with solutions beforehand. Politicians create a vast social welfare state. Dystopia then. Too bad we don't have robot politicians. Thank you.
Thank you very much indeed, and I know you're willing to answer some questions.
Yeah.
We've got some time, and there is a roving mic. So there's one question down here. Emma, start off right down here. Thank you.
Thank you. So at some point you mentioned that there's a long road in terms of algo development ahead of us to improve all this. Do you see that as the main, let's say, roadblock, or do you also see processing power and deep learning getting better with more layers than currently they use, and so on? So is it an algo development process you see as an improvement, or also processing power and deep learning in terms of number of layers?
Well, if you look back, say 30 years ago and now, in terms of the new development, algorithmic development hasn't really taken place. We use a lot of models that have been developed very long time ago. And what really changed the game is the availability of very large computing facilities as well as very large data sets. But there is, I think this is more a brute force way, just fill in more, build a large neural network, have a large data set and just train it forever until it gets what you want. I think we need to invest more in building algorithms. We can't expect in terms of, for instance, dialogue, that we have enough training data for every possible situation you can think of when it comes to speech. And yet, humans are extremely good in adapting to new situations, in learning from very little incentive. And this is something that I think we need to mimic in our algorithms. There is obviously a lot of work in this area, but I don't think it's sufficient yet.
Just another last one, promise. A parallel with the image processing, where I've seen in plenty of places where you have access to ready pre-trained models, right? Mm-hmm. Because there's so many pictures out there, and you can train a neural net forever, and then you've just got it, and it's very easy to take that and apply it to something else. Do you see that possible? Obviously, here might be some challenges, but to what extent would this be possible in the future?
Yes, so what we use a lot in language processing are what is called word embeddings. So this is some high dimensional vector representation of words that is trained on huge corpora. So then if you plot these vectors in a two-dimensional space, you can find, for instance, that mother and father are close in the space, queen and king are close in the space, and so on. And this is an example where you can train something from huge unlabeled corpora and get some semantic meaning. But again, there is still so much you can do with something that is very general. The key is how you then adapt these vectors to your particular situations. So for instance, if in a dialogue system for restaurant information, you would have, I want cheap restaurant and I want expensive restaurant, and something diametrically different. But if you look at these pre-trained vectors, cheap and expensive are almost the same. So then the trick is, how do you incorporate the small amount of knowledge that you have from your own problem?
Thank you. Yeah. Sorry, one over here. Yeah. Thank you.
Thank you. I'd like to come back to your point at the end. I'm one of those people who does worry about artificial intelligence, and I mean, you set out the problem, which is sort of with GDPR becoming very clear, the whole concept of who owns data. But I'd be interested in your thoughts about governance. That AI has huge potential, but arguably we need to have governance structures in place. And how do we think about that? Because if you think about Mark Zuckerberg giving evidence, it was pretty clear that the legislators who were asking the questions didn't really understand the questions they were asking. So, if we think of boards of companies, they're often older people who don't have this familiarity. If we think of politicians or legislators, they don't have this familiarity. And we all know of the danger of, I guess, algorithms which incorporate unconscious bias or malice. And so what would your suggestions be about governance systems to try and prevent that?
I'm not expert in governments or in security. Like I do dialogue modeling. But I, just as a layman looking at it, I mean, we can't have a handful of companies owning all our data, all our experiences, all our pictures and everything. That's just not right. So there is a lot of work, and there are people who actually specialize in this idea of how much you conceal. So, for instance, if you train a neural net, can you go back and find out exactly what a particular person has said, meant, or wanted? And I think what we need is to fund more this kind of research that will eventually protect us and protect our privacy and security. So I think that would be a better way to approach the problem. Just if we don't have experts, produce and breed experts that can deal with this problem.
Thank you. Any other questions? Right, well, Gillian, you have another
Sorry,
one.
I'd just be interested. We do a lot of work on women in senior roles, and I'd just be interested in your view. I mean, if I'm looking at the names here, I don't know, but just in sort of women in this space, in this sector, what the sort of gender split is.
It's very interesting. When I did my undergraduate degree back in Belgrade in mathematics and computer science, I never thought I was a minority in any way. I have many female friends from my undergraduate degree, but when I started my PhD, there was really a significant difference, and I don't think I was ever disadvantaged here in Cambridge for being a woman or anything like that, but it is a problem that we don't have equal gender representation in this subject, because it feels sometimes that we are building products that are mostly targeted towards one part of our society. So, but we can't really change that until the culture changes. And I'm trying to do that with, as part of Mary Edwards College, basically teaching young women, being a role model for them. But there is still, again, a long road ahead of us.
Thank you. Yeah.
So I'll just preface my question by saying that I actually make chatbots for my job on a daily basis, and all of this is entirely accurate in terms of like the level of expense and effort that we have to go to build huge trees with the systems that are available right now. And I just wondered if I made the assumption that when you were doing the reward-based learning, that you'd given it sentences that it could choose between?
Well, not quite. So if I go back to one of my previous slides, okay. Sorry, it's all the way. If I can do this, no, I can't. Okay, so what we have here, sorry. Okay, so what we have is a representation of the state. So this is some high dimensional representation where you are now in dialogue. And then a policy chooses these actions. Now this action here is in the same form like the input here, so it's in the semantic form. But there can be thousands of such actions. And then once you get that semantic form, we produce text. And this is done with long short-term memory network, which takes, which is conditioned on the semantics, produces words, and then feeds back words that it is producing. So that overall, at the end, it produces a meaningful sentence. And in that way, we can have more variability. Because if you put pre-cooked sentences and output, it becomes very boring to the user to listen the same output over and over again. Like this, if you do it in a statistical way, you can create more variability and more natural output. The problem is the difficulty to maintain the grammaticality of the output.
Mm-hmm.
Reference the speech recognition parts. What about other languages, and what about other world Englishes as well? We're basing the model on.
Yes, so that's a good question. That's exactly why I put that little star there. The speech recognition in Great depends on the corpora. And for English, we have a lot of corpora available, which is why this building a speech recognizer for English is nowadays relatively easy. but that's obviously not true for other languages. And if you look at some very small languages which don't have a lot of speakers, or for which there is not enough corpora available, the performance is very, very poor. And there is a whole area of speech recognition looking at this problem, which is called low resource problem languages. Now, even if you look at only, for instance, if you pick Chinese, and then you look at these problems like language understanding and language generation that comes after, the performance is still not as high as English, even for the same availability of the same size of the data set, even if the data set is of the same size, because English has a very easy structure. So although we don't really use anything that's language dependent in these models, it's simply neural network models, it's still much easier for it to produce a grammatically correct English sentence than a sentence, for example, in German, which is very morphologically rich language, or Arabic, which is really, really difficult. So there is obviously concern about using these systems in different languages.
Okay, thank you. I think we've probably got time for one more question. So if we just take, okay, sorry, you've got the microphone.
Oh, thank you.
Sorry.
Sorry if this is a poorly phrased question, because I'm quite new to this, but for your dialogue management part, you said you're using reinforcement learning.
Yes.
But from what I understand, if it's all in like just a big table, it's computationally quite difficult. So are you saying that you use like a neural network to approximate the
Q function? Yes. Yeah. So you can't, because this memory here, where is it? Come on. So this is a high-dimensional continuous vector. So you can't build a table. So what you do instead, you use reinforcement learning in combination with some function estimator. And this estimator can be a neural network, and it can also be something else. So in this work here that I presented, we used Gaussian process. But currently we have very good algorithms that work with neural networks and can achieve state-of-the-art results.
We'll take one more question, so I think perhaps the person in front, that would be great. Thank you.
I'm going to sort of offer an observation and invite you to respond to it, but try to ask a question as well. My observation is about this diagram and the reduction of the kind of squishy analog signal that is human speech into text at the first stage. My observation is that there's lots of feedback that's potentially lost by digitizing or encoding the speech and discarding the emotional potential information that accompanies it. And the question I'm going to ask is, when I know I'm speaking to an artificial intelligence, I adapt the way that I speak, right? Because I've got a goal, I want to set an alarm or check the weather forecast. Is anyone looking, or is there any research happening in the area of artificial intelligences deliberately identifying themselves for ethical or purely practical reasons in standardized ways, I wonder?
Okay, so I think this is 3 questions.
It probably was.
So the first question, yes, there is a lot of information loss. The problem is we didn't really know how to incorporate or how to accurately estimate emotion. Ideally, we would want to have another emotion estimator here that takes the same speech and then possibly the text as well, and then that feeds into, as a feedback signal into reinforcement learning algorithm. And this is something which I think will happen soon. Now, the second question that you said is the question of entrainment. The fact that you adapt to an artificial system, and this is indeed something that people do a lot. So when we run these experiments, we often have people saying cheap, Chinese, center, And the problem is that these systems are not trained on this kind of data, so they expect you to say full sentences so that they can understand. And we oftentimes had to make people please talk to it as if you would talk to your friend, because that is when the system actually has the best chances of giving the right answer. And the third problem is the problem of policy. And I think there are people who are looking at this issue of that the system should disclose themselves. And I think it's gone. Google has revealed their new product called Duplex. Where you can basically make an automated call to your hairdresser or your restaurant to book a restaurant and so on. And I'm sure these places don't employ somebody to actually answer automated calls. So I'm sure that this would, if it hasn't come up already, it will be an issue.
Okay, thank you very much. I think we must finish there because we're supposed to finish at 7 and we've gone slightly over, but it's good that there are lots of questions coming up. I know quite a number of you are booked in for dinner, and those who are booked in for dinner have a chance to ask Milica perhaps over drinks beforehand any questions you might have. But in the meantime, could we please show our appreciation again? Thank you very much indeed. Really